This video shows the working of the clock and the stepper in an adding operation. It is the simulation part of the clock and the stepper video of the How Computers Work Building Scott's CPU YouTube playlist. We use the Circuitverse simulator and the circuit is available in the link I leave in the description. Here you see the simulation circuit. We want to show how the clock and the stepper work in an adding operation, giving the right timing to the registers. Here you see the stepper, which has a cycle of 6 steps, in which we have to fetch, decode, and execute an instruction. Here you see the clock generator, which also generates clock E and clock S, which are used to create the right enable and set pulses to the registers, in order to move bytes from a register to another. Here you see the two registers in which there are the 2 bytes that we want to add. And here there are the ALU with its registers, accumulator, TMP, and also bus 1, which we have described in previous videos. So this is our simulation circuit. Here we have the stepper with its 6 steps. Here we have the clock generator, which also generates clock E and clock S. And this is a counter which I use to control the stepper because I want just to perform one cycle. So step from 1 to 6, just one step per cycle. Otherwise, I keep adding the content of my 2 registers over and over, I don't get the result I'm expecting. So I need to control for this simulation the stepper. Here there are the enables AND gates, and here there are the set AND gates. The enable AND gates are connected to the clock E, and for our simulation we use the steps 4, 5 and 6 to perform our addition. In general, in Scott CPU, steps 1, 2 and 3 are used to fetch the instruction in the instruction register, and the other 3 steps are used to decode and execute the instruction. So we use to perform the addition step 4, 5 and 6. Of course, for example, steps 4 in our case is connected with an input of the AND gate, which creates the pulse, the enable pulse to the register R0. So in order to create the right enable pulse to a register, we put in AND the clock E and the proper step. So if we want to give this pulse in step 4, we connect step 4 with this AND gate, which the output goes to the enable of the register R0, and so on. I mean, if I want to give a set pulse to a register, I have to put in AND the clock set and the right step. So in this way, I'm sure to create the set pulse in the right step. So in our case, we want to add R0 to R1 and put the result in R0. So the output of the AND gates, the enable AND gates and set AND gates, are connected to the registers we have here in the circuit. So the enable AND gates are connected, of course, with the enable inputs, and the set AND gates are connected with the set inputs of our registers, like temp, like accumulator, RO, and R1. You see here there is a bus, here there is just an enabler to put a byte in the bus and to acquire the byte in the 2 registers. So I can put 2 different bytes in these 2 registers and perform the addition. Here there is the temporary registers. Here there is the bus 1, which we not use in this simulation, so we leave this control bit to 0. And here there is the ALU. The ALU has the A input directly connected to the bus, and the B input connected to bus 1 and the temporary registers. The output is always connected to the accumulator, and the accumulator is connected to the bus. So what I have to do here is put the content of RO in the bus, giving an enable pulse, and acquire this content in the temporary registers. Then free the bus and give an enable pulse to the register R1, putting the content of R1 in the bus. So we have the content of RO or R0 in the B input of the ALU and the content of R1 in the A input of the ALU. We leave the opcode to 0. In this way we perform an add operation, and in this way the output of the ALU is immediately gives immediately the result, because the ALU doesn't need a clock, is a combinational circuit, and then I have to acquire the result in the accumulator, giving us set pulse to the accumulator. This is performed in the fifth step. In the last step, I put the content of the accumulator on the bus and I acquire the content in the RO. So in this way, I performed RO plus R1 and I put the result in the register RO. So let's see how to do this. So in order to do what I just described, we have to connect the steps to the right AND gates. So first I want to put the content of R0 on the bus, so I connect step 4 to the AND gate, which gives the enable pulse to R0. Then I have to acquire the content of R0 in the temporary register, so I connect the step 4 to the AND gates, which gives the set pulse to the temporary registers. Then I have to free the bus, but this is a pulse, so enable and set came back to 0, so the bus is free after this step 4, and then I have to put the content of R1 in the bus. So I connect step 5 to the AND gate, which gives the enable pulse to R1, and the step 5 also is connected to the AND gate, which gives a set pulse to the accumulator, because in this time, in the step 5, the ALU has both the byte which it has to add, because there is in the temporary register the content of R0, and the content of R1 is in the bus. So immediately the output of the ALU gives the result, and I acquire this result giving a set pulse to the accumulator registers. So at the end of step 5, the result is inside the accumulator register. Now in the step 6, I have to acquire this result in R0. So I give basically a set pulse to R0 and an enable pulse to the accumulator to put the content of the accumulator on the bus. So step 6 gives here is connected to the AND gate, which gives enable pulse to the accumulator register, and step 6 is connected to the AND gate, which gives a set pulse to the RO registers. So now we run the simulation. So first we put some numbers inside the two registers. For example, we put the number 3 inside the R0 register. So we put the number 3 on the bus with this enabler, and we acquire this number inside RO, giving a set pulse. I can give a set pulse with this OR gate, which is not in the Scott CPU, but I have to use for this simulation. So I give a set pulse, and we free the bus. Let's see if what there is inside RO. We put the enable of R0 to 1, and we see there is the number 3 inside the register R0. Oh, sorry. We free the bus. And now we put the number, for example, 2 inside R1. So we put the number 2 on the bus and we give a set pulse to R1. So we free the bus. Let's check what there is inside R1, giving an enable pulse, and we read the bus, there is the number 2. So we free the bus. So now there is the number 3 inside R0 and the number 2 inside R1. So we expect to find the number 5 inside R0 at the end of our simulation. So now let's go to run the simulation. And in order to run the simulation, I give a pulse here in this counter, and this allow just one cycle of the stepper. In this way, I perform the adding just once. So I give this, and you see there is just the light green run in all the steps and stops at the step 1. So we go to see what there is inside R0, putting the content of R0 on the bus, giving an enable pulse, and we see there is the number 5, because this is the first bit, the second bit is 0, and the third is at 1, so this is the number 5. So it worked. We free the bus again, and we can see now the timing simulation. So for the timing simulation, we open the timing diagram, and we have put all the probe in the right line, and we see giving a reset pulse here, we perform a step cycle, and we see if all the signal worked in the right moment. So we stop. So here there are the 6 steps. Here the first, which is a strange behavior, but just because I have to stop the cycle, so it stops in the step 1, so it is at high level always if the cycle is not running. Here there is the 4th step, and we start to give pulse in the 4th step. In particular, we give the enable pulse to the register R0, and we give the set pulse to the register TMP. This is performed in the step 4, as we wanted to do. In the step 5, we give an enable pulse to the register R1 and a set pulse to the accumulator. In the step 5, the ALU perform the addition, and we acquire the result of the addition with this set pulse in the accumulator. Then in step 6, we give an enable pulse to the accumulator to put the result on the bus, and a set pulse to the register R0 to acquire and save the result in the register R0. And this is the timing diagram. We see all the line and the signal worked well. Please leave me a comment, let me know if you liked this video. Make sure you put a thumb up, click the notification bell and subscribe to my channel.